Good evening, everybody. Welcome. It's beautiful, snowy Wisconsin evening. I'm delighted to introduce our speaker tonight, Cris Moore. I'm being reminded to remind you that on February the 18th, we have another marvelous public lecture on the future of gaming in education. And that's going to be given by one of our own internal Wisconsin Institute for Discovery research groups, the Games, Learning, and Society group. So I think that'll be a lot of fun. Okay, so just a little bit of a recap since it's the first lecture of the year. This series is about collective computational phenomena. And over the course of the series, we've had an extraordinary range of topics, right? Consciousness, economics, decision-making, swarming, how you would program the internet, social computation, epidemics, and the nervous system. And it looks, on the surface, completely incoherent, right? But if you look slightly beneath the surface, you'll see that they're all about asking, how do distributed asynchronous decision-making systems work? That's the unifying concept. And how do they produce, without any one unit having the full solution, a solution that makes sense at the aggregate level, sort of an emergent function. Now, at the core, right, of all of those systems is communication. Because if you have all of these distributed agents, they need to tell each other somehow what they know, because they need to produce this coordinated aggregate function. And that's the topic of today's talk, issues relating to communication. Now, historically, when you think about communication, you assume that the signaler and the receiver are aligned in their interests and that no third party has malign intentions with respect to their exchange of information. But we live in a world where we know that's not true, right? And so most of us are distributed agents with respect to our banking, with respect to our online purchasing, and there are individuals who would like to intercept our emails and our phone calls. And so we have to be ingenious in the way we encode the information so as not to allow it to be intercepted. And so cryptography, that's a very mathematical field, a very foundational field, is one of those mathematical fields that's also extraordinarily practical. It's a good example of where fundamental mathematical science is also of enormous practical value, immediately. The person who's going to guide us through this sort of both social and scientific and mathematical field is Cris Moore. He's a friend and colleague from the Santa Fe Institute. He got his BA in physics and mathematics from Northwestern, his PhD in physics and dynamics from Cornell. He worked on some interesting, weird orbits in three-body systems with Phil Holmes. In 2000, he joined UNM as a professor in computer science, maths, and astronomy. And in 2012, he became a full-time resident professor at the Santa Fe Institute. His work includes important results in mechanics, network theory, computational complexity, and quantum cryptography. Recently, he published an amazing book. The book was co-authored with Stefan Mertens, and it's called The Nature of Computation. And I just want to read to you a review of this book. No, and it's not a negative. I would do that to him, but I won't do that to him. And it was by a professor at MIT, Scott Aronson. He said, "To put it bluntly, this book rocks. It's 900 pages of awesome. It somehow manages to combine the fun of a popular book with the intellectual heft of a textbook. So much so that I don't know what to call it. But whatever the genre is, there needs to be more of it." And so I'm delighted to welcome Cris Moore.
Thank you very much, David. It's an honor and a pleasure to be here. So thank you very much to Jessica and David for inviting me. This is a gorgeous building. I love how it provides this outward-facing educational component as well, and not to mention the is it Mesozoic garden, which I think was very pleasant. I didn't walk in it, though. All right, so it's widely thought that one of the great leaps upward in the evolution of the human species was the invention of speech, which allows us to convey ideas and concepts from one individual to another. So the next question is how you can convey ideas across vast spaces of, vast gaps of space and time. I guess there's more than one way to do this. You could have a really good oral tradition where people are extremely good at memorizing things and repeating them, and that's how some cultures do it. But what a lot of other cultures invented was writing. And so this lets us read the thoughts of people who are thousands of miles away or who lived thousands of years ago. But what if what you want to write is something intended only for your eyes and the eyes of your friends? Then you need some kind of system of your own. There are lots of examples of this, and I think the idea of secret writing is almost as old as writing itself. One of my favorite examples is the Christian mystic Hildegard of Bingen, who also wrote a lot of beautiful early polyphonic choral music. And she invented a language and an alphabet called the lingua ignota, or unknown language, in which to record her revelations. Another fun example is that Beatrix Potter, from the age of 15, wrote her journal in a secret alphabet, presumably so she could be more candid about certain people in case her journal fell into the wrong hands. So, of course, another famous person who didn't want his writings to fall into the wrong hands was Julius Caesar. So I expect almost all of you have heard of what I'm about to say. By the way, nothing in this talk involves any mathematics beyond the 6th grade. I hope you brought your kids. If for some reason you didn't bring your kids, you can go home and I'll give you lots of things tonight that you can tell your daughters and sons. So anyway, Caesar's idea, as you probably have heard, is to take the plain text, that's what we call the true message that we're trying to send, and encrypt each letter by shifting it 3 places forward in the alphabet. So A becomes D, B becomes E, and we treat the alphabet as a circle, so X, Y, and Z go around and become A, B, and C, so that this utterance, which I think Caesar unfortunately did not have the time to encrypt, the E would become H, T would become W, and so on, and that would be the ciphertext, the encrypted version. And of course, to decrypt it, you just shift things backwards again. Now, one drawback of this system is that if you consider all codes of this kind, there are really only 26 possibilities. There are only 26 ways to adjust this decoder ring, or 23 actually in Caesar's day. So if you know that it's this type of code, then you only have 20-something things to try, and you, the eavesdropper, as the attacker, will be able to successfully decode the message. So if we want to have a more elaborate cryptosystem, we can follow the Kama Sutra, which recommended that people, especially women, learn the art of secret writing. So they recommended a more elaborate code where rather than simply shifting each letter forward in the alphabet, we completely scramble the alphabet. And so if this is our plain text, then we would, each letter would get mapped somewhere so that, E would go to H and so on. And then what you and your friend need to know, you both need to have a copy of the scrambled alphabet, and so to decrypt the message, you would look things up in reverse. So one benefit of this code, on the one hand, you and your friend need to share more information, not just the number 3, as in Caesar's code, but this entire scrambled alphabet. On the other hand, what you get in return for that is a much larger set of possible codes. There are 26 letters to which we could send A. After we choose which one A will become, there are 25 possibilities for which one B could become, and so the number of possible codes is 26 times 25 times 24, et cetera, which is a nice big number. So this kind of substitution cipher, as it's called, is certainly much more secure, much harder to crack than Caesar's code, but not impossible. So the 9th century mathematician and cryptographer Al-Kindi invented something called frequency analysis. So we're going to take advantage of the fact that in every language there are certain letters that are much more common than others. In English, these are E, T, A, and so on. So at least if you have a long enough message, the most common letters probably correspond to those, and that gives you an in. There are other things. Only certain letters appear twice next to each other, L, L, E, E, and so on in English. And then there are really common diagrams, like Q is almost always followed by U. It also helps if the person who you're eavesdropping on has kept the spaces and punctuation, as in the crypto quip in certain syndicated newspapers. So if I show you this message, for instance, you might guess that that NN is probably really an OO. And once you know that, well, this is either on or of, and this one-letter word is certainly either I or A. So let's make a couple of lucky guesses about that. This thing here, blank OO, must be, that J must really be a 2. And this thing with 2 O's in the center is probably either the word look or the word good. And pretty soon we can fill in my favorite Mae West quote. All right, so now you know how to solve these puzzles. So even though we had an enormous number of possible codes, we were able to use this frequency analysis to break it fairly quickly. So if we want a secure cipher, at least once we're past Al-Kindi's day, we need to do something which doesn't just use the same scrambling of the alphabet for every letter. So here is a cipher invented by Thomas Jefferson. Actually, it was invented independently several times. Each of these disks does a different scrambling of the alphabet. And what you and your friend know is in what order these disks should appear on this rod. So this is much more complicated because we're not simply doing the same thing over and over to the alphabet. And in fact, I was surprised to learn this morning in my hotel room as I was drawing on Wikipedia in preparation for this talk, that this cryptosystem was used by the United States Army between World War I and World War II. So it was considered pretty secure until quite recently. Now, if you use the same ordering of the disks over and over for multiple messages, then you start to get vulnerable to some statistical attack, but it's still fairly difficult. All right, so a similar idea is behind the Enigma Machine, which many of you know about, perhaps from watching the movie The Imitation Game. So the Enigma Machine has rotors inside it that turn each time you type a letter on the keyboard, and in fact, which letter you type changes which wheels turn. So literally, you're changing the code after every letter, and how you change the code depends on the letter of your message. So, so we've all heard of Alan Turing, but another character who deserves to be remembered is a Polish mathematician and cryptographer, Marian Rejewski, who just before the Nazis invaded Poland, provided some very important intelligence, shared some very important intelligence with the British about the inner workings of the Enigma Machine. And this helped people, including Alan Turing, to crack the Enigma, which of course was a vital part of the Allied war effort. And again, I hope many of you know this, but I think it's important to recall that even after making this enormous contribution to mathematics and early computer science, Alan Turing was persecuted for his homosexuality and sentenced to a horrible chemical regime which drove him to suicide. In 2009, the Prime Minister of England apologized for this, sadly a little late. I should mention that Alan Turing is very close to our hearts for multiple reasons, not just his foundational contributions to computer science, but to many other fields of what we now call complex systems, including the first study of pattern formation in the way that, how do tigers get their stripes and leopards get their spots, and how do developing embryos of insects and so on turn into these segments of a thorax, and there are other parts that I don't know what they're called. So he did some very important early work on pattern formation. These things are still called Turing patterns. All right, so is there any cryptosystem which is truly impossible to break? I mean, all of the things we've talked about can be broken using more and more clever statistical analysis. So there is such a cryptosystem, but you don't get it for free. It's called a OneTime Pad. So here's our plain text. I want to send you the secret date on which tonight's seminar will take place, January 21st, 2015. Now, here is our secret key, or the OneTime Pad. It's a sequence of completely random digits. And in order to encrypt my message, I add them digit by digit to the message. So, 0 plus 1, that's not 5. Oh, okay. All right, sorry. All right. You know, I gave this talk on an earlier date before, and I guess I didn't update the... yeah. Oh, okay, but I do want to point out one of them which is right, maybe by coincidence. All right, so 0 plus 1, that should be 1. 1 plus 4, that should be 5. 2 plus 1, that should be 3. Okay, but this 2 plus 9 is 11, right? But I'm only going to keep the ones digit. So 2 plus 9 is 1. This is called addition mod 10, so I'm adding without carrying. I'm only keeping the remainder when I divide by 10. So you happily have a copy of this same pad, so to recover the original message, you just subtract off the things I got, which, if this were correct, would give that. All right. Okay. Yeah, I used it and then I ate it, right? Because the thing is, so the good news about this, but please forgive me, the good news about this code is that if this pad is completely random, then no matter what the message is, no matter what the plain text is, the encrypted version will also be completely random. No matter what you start with, if you add totally random stuff, you get totally random stuff. So there's absolutely no pattern that an eavesdropper can use. You've destroyed all the information, but then you undestroy it when you decrypt the message. There's an important caveat, though. You should never use the same pad twice, okay? So this is a very secure cryptosystem, but it is expensive in terms of the amount of shared information. If I want to send you a 1,000-digit message, I need to use up 1,000 digits of secret key. And we must never use those again, which means that we must occasionally meet to share more copies of the secret key, to share fresh random bits. And during the Cold War, both sides did a lot of this with tiny books full of tiny digits, sometimes rolled up inside a walnut shell. Okay? So you and I have to meet in Gorky Park, or I have to hide a walnut shell, under a bridge somewhere. And of course, as you can imagine, if you get caught crossing the border with a walnut shell full of a tiny rolled up piece of paper full of tiny digits, you might get into trouble. So while this form of cryptography is perfectly secure, it also requires a lot of, as we say, physical security. We have to be able to share physical stuff to make this work, and we have to do that on a regular basis in order to communicate, which carries its own risks. Alrighty. Okay, so all of the cryptosystems that I showed you at the beginning had, and even the OneTime Pad, had a disadvantage. They encrypt one letter at a time. This letter of plain text turns into one letter of encryption, the next letter turns into the next letter, and so on. So you've seen a lot of movies. I wasn't able to find a good clip, but you've seen a lot of movies where some hacker is sitting and she's going blah, 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 on the keyboard, and then she gets the first letter of the password right, and the others are stars or something, and she goes blah, 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 and the next one turns correct, and then the next one and the next one. Well, this would be terrible. This would be a very insecure cryptosystem if an eavesdropper could figure out one symbol at a time. A much more secure cryptosystem would be one where every letter of the encrypted message depends on every letter of the plaintext. In other words, you don't want your eavesdropper to get anything right until she gets everything right. Okay, you don't want them to be able to nibble away at the message one letter at a time. Rather than this, you want something like that. So we want some complicated mathematical relationship between the plain text and the encrypted message. And how might we be able to get that? So first, a little bit of that 6th grade math I promised you, or maybe 4th. So we're going to talk about cyclic or modular arithmetic. So a number mod n is the remainder I get when I divide by n. So for instance, x mod 10 is the ones digit of x. 53 mod 10 is 3, because if I divide by 10, I get a remainder of 3. So for instance, as I said before, 2 plus 9 is 1, mod 10, okay? Because the remainder of 11 after we divide by 10 is 1. So of course, we're used to this, even if we don't think we are. So for instance, if it's currently 11 o'clock, then 3 hours from now, unless I'm in the military or in Europe, I don't usually say it is 14 o'clock. I take the remainder mod 12 and say it's 12 o'clock. 2 o'clock. 2 o'clock. We also use modular arithmetic without saying so when we treated the alphabet as a circle in Caesar's cipher. So if A is 0, B is 1, C is 2, and so on, when I add 3 to x, I get 23 plus 3 is 0. 24 plus 3 is 1, 25 plus 3 is 2, because I'm taking the remainder mod 26. Multiplication mod 5 is really interesting. In the mod 5 world, 3 is 1/2, because 2 times 3 is 1. Get it? Okay. Finally, if I take the population of Santa Fe and take it mod 1000, I get the last 3 digits after the thousands digit. All right? Now you know all about modular arithmetic. Good. So here is the cryptosystem on which most electronic commerce, or now I should just say most commerce, is based. So Bob wants to send a message to Alice. That's Robert the Bruce from A Scottish Banknote. That's my favorite illustration of Alice, not the wimpy looking one where she's running from the cards. She looks a little more powerful in this one. I like that. So Alice wants to make it possible so that anyone in the world can send her a message, but only she can read the message. So she's going to have a public key and a private key. Her public key is what she puts in her email signature or on her web page. And these are 2 numbers. We'll call them E and N. So if Bob wants to send her a message, M, which we'll also think of as a number, what does he do? He raises it to the power E. He multiplies it by itself E times. And then he takes the result, mod N. And then he sends that number to Alice. So let's do an example. Let's say E is 3 and N is 1,000. And let's say Bob wants to tell Alice, meet me on the 413 train. Okay, this is his secret message. He raises it to the 3rd power, multiplying it by itself 3 times. He gets this, and then he takes this mod 1000, which picks out these last 3 digits, and he sends Alice the number 997. Okay, that's how he encrypts this. Well, now, how is Alice supposed to decrypt this and get the original message? Alice knows an interesting fact. This is just a review of the previous slide. So here is Bob's encrypted message. Here's his original message, 413. Alice knows a fascinating fact. She knows that if you take this number and raise it to the 67th power, and again take it mod 1000, you'll get the original message back. Let's try it. Here's the 67th power of 997, and there is, at the last 3 digits, 413. So it worked. And this will work whenever Bob's message is not a multiple of 5 or it also has to be odd. Luckily, 413, the time of his secret train, is neither of those. All right, I'm not going to explain to you today why 67 is the right power to use to undo this encryption. I'll leave that to another lecture. But so the idea is that Alice publishes these numbers 3 and 1000 so that anyone can encrypt things, but she keeps to herself the number 67 that allows her to decrypt it. So this is why it's called public key cryptography. It's an asymmetric process. If Alice wants to talk to Bob, she uses his public key, okay, and then he uses his private key to invert it. Now, if you're nervous about, South Korea and the NSA and so on, you'll use very large numbers for E and N, and not just something only 3 digits long. Okay, good. So how might we crack this? So what would an eavesdropper like to do? An eavesdropper would like to say, well, if Alice's public key is raise things to the 3rd power and take the mod 1000, I can figure out that her private key is the number 67. So the question is, how do we do that mathematically? How do we figure out that inversion? It turns out that, so in other words, how do you get this, I called this decryption exponent D. How do we get D if we're told E and N? Well, it turns out that you can do this if you can factor this number N into primes. So for instance, 1000 is 2 times 2 times 2 times 5 times 5 times 5, and that's the smallest pieces we can factor it into with multiplication. So if you can take these numbers and if you can take large numbers and break them down into their prime factors, then you can break RSA, public key encryption. Okay. So factoring doesn't seem so hard, does it? I mean, after all, multiplication is easy. So we all learned in grade school how to multiply big numbers. If 2 numbers have n digits each, then we know that we can multiply them with about n squared work, right? Here's the classic method. We do this, and then we just have to add this stuff up, and you can kind of count the amount of work we have to do just by the amount of ink that we use. And if this is an n-digit number and this is an n-digit number, the total amount of stuff we have to do is about n squared. So this tells us that multiplication is in a complexity class that computer scientists call P for polynomial, because functions of n, which consist of n raised to the something, n squared, n cubed, these are polynomials. So we don't think of, I mean, this might be tedious, but you can do it, even if you were multiplying 200-digit numbers with enough time and enough pencil, you could do it. On the other hand, what about breaking a large number down into its prime factors? So this is Father Mersenne, who was interested in certain numbers. He was interested in numbers that are powers of 2 minus 1, so 2 to the 67, there's 67 again, I don't know why, minus 1 is this large number, and Mersenne thought it might be a prime. He didn't see any small numbers that it could be divided by, so he thought maybe it had no factors smaller than itself. And then a gentleman named Frank Nelson Cole gave a famous lecture in which he tediously on one blackboard raised 2 to the 67th power and got this number, and then he tediously on another blackboard multiplied these two numbers together and got the same thing, and then he sat down to a wild round of applause. So how did he find these numbers? According to him, it was a pain in the rear, or what he actually said was, it took a month of Sundays. So, you know, it's one thing to multiply these two numbers together, it's tedious but doable, but it's another thing to think about what are all the possible numbers that could have gone into this. It's not clear how to go about that without some horrendous search process. So there's another complexity class that computer scientists call NP. The N stands for non-deterministic, but this is just a historical accident. What it really means is that this is the class of problems where I can check a solution not without too much trouble in polynomial time. So I can certainly check this by doing this multiplication. But that doesn't mean I can find solutions. It means that it could be a bit like finding a needle in a haystack. If you find something in a haystack, you can check to see if it's a needle by pricking your finger, but if the haystack is large, that doesn't mean you can find one or even tell whether there is one. All right, so in fact, we think, although we don't know, that there is no polynomial time algorithm for factoring large integers. We think that it's a very difficult problem. We don't know that. We might just not have been clever enough so far. Okay, but so far nobody's been able to do this. So we think factoring is hard, and therefore we think that breaking RSA encryption is hard. Okay, that's why we all blithely spend all our time on the internet buying stuff without too much fear of our credit cards being stolen, interfered with, or anyway. We should probably be a little more fearful, but anyway, we think that factoring is hard. All right, so what is this business about polynomial time, exponential time? Well, the point is that computer scientists are interested in how a type of problem gets harder as the particular example you're struggling with gets bigger. So before we saw that if you want to multiply numbers that are n digits long, you can do that in n squared time. In fact, that's not the fastest way, but I don't have time to tell you about that. Anyway, so here's the function n. When n is 1, it's 1. When n is 2, it's 2. And n is 3 is 3. And it does not grow too badly as n grows. Here's the function n squared. It doesn't grow too badly. It's getting bigger. N cubed doesn't grow too badly. It's getting bigger, but not too fast. We can handle fairly large problems. But here's an exponential. So you may have heard of the great fable where the inventor of chess, the Raja says to the inventor of chess, "Chess is such a great game. Thank you so much for inventing it. What can I give you in return?" And the inventor says, "Well, people in my village are rather hungry, so I would like a chessboard with 1 grain of rice on the first square and 2 grains on the next, and 4, and then 8, and then 16, and 32, doubling each time." And the Raja says, "No problem. Call the royal chamberlain, bring out the rice." And the problem is that by the 20th square, we have more than 1 million grains. By the 30th square, we have more than 1 billion grains. And by the 64th square, we have more rice than there is in the Milky Way, even if there are other places with rice. So if a problem's difficulty grows exponentially, we can't really hope to solve it anytime soon. I mean, this is not just more than the amount of rice we have in the world. This is more than the number of steps that any computer could perform within our lifetimes. So for instance, here's a little plot. This is a logarithmic scale. So here's n. So this says that here we're assuming that we can do 1 million things per second, which is pretty reasonable. And if the difficulty of a problem grows like n or n squared or n cubed, where n is the number of digits or whatever it is we're dealing with, well, we can easily handle large values of n in less than a minute. On the other hand, if the difficulty grows like 2 raised to the n, 2 times itself n times, then as soon as n is 90, the stars will burn out before we can solve the problem. So next year, your computer will be twice as fast as your computer is this year, but that won't help very much, because 2 times 90, 2 raised to the 90, I'll double that. Guess what? Now that's 2 raised to the 91. So if before you could handle a problem of size 90 just when the stars burn out, now you can handle 91. Whoop-de-doo. So if a problem gets exponentially harder as n increases, then even this steady doubling in the speed of a computer will not help us solve it very much. So this is why theoretical computer scientists tend to draw such a strong distinction between polynomial time and exponential time. Roughly speaking, if we have to search through all possible solutions, it's going to take exponential time. If we have some insight that lets us skip through all that lets us zoom right in on the needle in the haystack if there is one, without having to go through all the hay, then the time is polynomial. All right. So, now there's another kind of algorithm or computer program that not enough people have heard of. In my world, it's all the rage, but maybe you haven't heard of it. It's a program which makes random choices. It flips coins. So you might imagine that a typical computer program takes the input and follows some steady deterministic path until it arrives at the right answer. A randomized computation might flip a coin, generate some random numbers, and do one thing or another thing. And then each path will have some probability of starting from that initial state of the computer where it's given the input to the final state where it produces the output. And the total probability that it gives the right answer is the sum of the probabilities of all these paths. Now, I think this is unfamiliar because you might think that randomness is just a source of noise and annoyance and mistakes, but actually, in many cases, it's a source of computational power. And there's a lot of problems, including telling whether a large number is prime, for which the best algorithm we know of makes random choices. So if this isn't already in your undergraduate curriculum, you must put it there. All right, but probabilities just add up. If there are two ways that something can happen, the total probability it happens is this probability plus that probability. Let's talk about quantum stuff. So, as you may know, in the quantum world, we don't just have probabilities. We have things called amplitudes, which is a little confusing, but they have both a size and a phase. And what does this phase mean? Well, a laser is so bright because all the light waves in it are in phase. So they all add up, all their peaks are in the same place, all their troughs are in the same place, and this makes a very bright beam of light. But a noise-canceling headphone works by producing sound of roughly the same loudness and frequency as, the annoying person next to you on the airplane, but with opposite phase so that it cancels out. So in the quantum world, things don't just add up. They might add or they might cancel depending on whether they're in phase or out of phase. So this is something which occurs even in the classical world whenever you have something which is a wave. So there used to be this big argument about whether light is a wave or a particle, except I think they said oscillatory or crepuscular, if I remember correctly. Of course, it would be great to go back in time and tell them it's both, haha. But so a beautiful experiment in 1801 really confirmed that light is a wave. So this guy, Thomas Young, sorry, giving everything away. Let light at a particular frequency after coming through a prism or something come in through two holes, and over here he found that depending on where we were, we got a light spot or a dark spot, and the point is that there are places where these two waves arrive in phase, producing a light spot, but there are other places where they arrive out of phase and cancel out. You can do this with water waves as well, but what's more surprising is that this happens even if you send in one particle at a time. One electron, it hits a photographic plate or a TV screen, and then another electron, and then another electron. Electrons will actually interfere with themselves. There are two, they can come through this way or that way, and yet sometimes they kind of do both or neither. It's a little confusing. So here's what's going on. There are two ways for the electron to come through this screen, and as it comes through, its phase is rotating in time. And whether it arrives with the same phase or a different phase depends on the length of this path. These two paths have the same length, so it arrives here from this path and this path with the same phase, so these things add up, and it shows up there a lot. But because this path is a bit longer, it has time to rotate a little bit more, so that by the time it gets here, it arrives with this phase, whereas on this path it arrives with this phase, and so, bizarrely enough, there are two ways for it to get there, and it never shows up at all. Okay? So this is odd. And so this is the idea behind quantum computation. We're going to arrange this kind of, as we call it, constructive interference and destructive interference, so that different paths leading to the right answer will happen with the same phase, so that we'll get a large probability of getting the right answer, but that the different ways to come up with the wrong answer will cancel each other out, so that we don't get the wrong answer, or at least not very often. So that's the idea behind quantum computation. All right, so now I will show you how quantum computers can factor. So in 1994, Peter Shor came up with this algorithm. It was based partly on some previous mathematics. Here's the idea. I want to factor a number n. I'm going to do the following experiment. I'll choose some other number, x. Turns out I should choose it randomly. And I will look at the powers of x, 1, x, x squared, x cubed, but take them all mod n, and I'll ask, when does this sequence repeat? So let me show you an example. I want to factor the number 15 and learn how to write it as the product of two prime numbers. I'm going to look at the powers of 2 mod 15. I'll start with 1, I double and get 2, and then 4, and then 8, and then 16, but 16 is 1 mod 15. Okay? So this sequence repeats, 1, 2, 4, 8, 1, 2, 4, 8. It repeats every 4 steps. Good. What does that mean? It means that the fourth power of 2 is some multiple of 15 plus 1. I know it's 15 plus 1, but pretend you don't know that. Okay? Well, that means that if I subtract 1 from both sides, 16 minus 1 is some multiple of 15. Well, 16 is the square of 4, and 1 is the square of 1, and now here's the 6th grade math. The difference of two squares can be factored. X squared minus y squared is x minus y times x plus y. So we can factor this as 4 minus 1 times 4 plus 1, and lo and behold, that's 3 times 5. And we factored 15. So if Alice was using 15 as her RSA key, we can now read all her email. All right, and indeed, this algorithm has been carried out in the laboratory with a quantum computer that has 4 bits of memory. So we're already on our way. All right, now you might think, well, come on, you've just shown me how to factor numbers. Why don't I just do this and read all the credit cards I want? Well, the problem is that this list of powers could go on for a very long time before it repeats. So if you start just writing down powers and waiting to see when it comes back to 1, it could take an astronomical amount of time. If n, the thing you're taking this remainder mod, if that's 1,000 digits long, you could end up counting up to something in the neighborhood of n, or square root of n, which would take you too much time. All right, so how are we going to do this? Well, here is Joseph Fourier. And you may have heard of Fourier analysis. So what does Fourier analysis do? It is the heart of all modern signal processing. And what it does is it breaks any kind of signal, any kind of sequence, down into a sum of frequencies. So if we have this thing wiggling here, going up and down, well, Fourier would say, no problem. That is mostly this nice steady beat, this sine wave, plus a smaller amount of this faster one, plus a yet smaller amount of this still faster one, and indeed, you can take any sequence at all, any function, and divide it up into these oscillations. And this is what your ear does when someone plays a chord, and you can hear that it has a C and E and an F in it. You have little things in your ear that vibrate at different frequencies, so they resonate with different frequencies, and that lets you pick out these all the fundamental tones. So guess what? I'm not going to show you the details, but a quantum computer can sense these frequencies, these periodicities, in a sequence of numbers, even if that sequence is exponentially long. First, you kind of store the entire sequence in the computer, and miraculously, you can do that very quickly. If we go back to this, we looked at all these powers, I set my computer up so that it is in a superposition, as we call it, of all possible values of which power of x we want, and then in a single stroke, I compute all these powers of x simultaneously. That's pretty cool that we can do that. But what's more interesting is that then, given that sequence, I can quickly and easily find its frequency, its periodicity. And that's the heart of the algorithm. So this shows that quantum computers can find this periodicity in this sequence of powers. That means they can factor large numbers. That means they can break RSA. And that's why a number of government agencies started funding lots of work in quantum computing shortly after the discovery of Shor's algorithm. Okay, good. So, well, if quantum computers are around the corner, and I don't think they're right around the corner, but I do think we'll see them in our lifetime, are there any cryptosystems we can use that they can't break? I mean, are they just these magical devices that can solve any problem at all? Or maybe there are problems that even they can't solve. So just as currently we believe that RSA cryptography is secure because we believe that factoring is hard for today's computers, maybe we can come up with a problem which is hard even for quantum computers and use that to come up with a cryptosystem that even they cannot crack. So let me tell you briefly about one possibility, which has to do with what are called error-correcting codes. So the word code here doesn't really mean secret code, although it will later. So the idea of an error-correcting code is that we have a bunch of possible messages. So here I have this string of 7 bits, this string of 7 bits, this string of 7 bits, and notice that each of these is quite different from the other two. Well, this series has been cleverly designed so that even if I add combinations of them up, and I'm adding mod 2, 1 plus 1 is 0, even if I add them up, all the possible strings I can get are different from all the other possibilities. So here, I've added this one, the second one, to the third one, and I've gotten this one. And if you look at all the possibilities you can get, they're all different from each other by a lot. So each of these combinations is different from all of the others in at least 4 places. This is good news, because if we use this to store music on a CD, and our CD gets a little scratched up so that a few bits of the music are wrong, we can fix that and have the CD continue to play. All right. By the way, the stuff that CDs are made out of turns out not to last nearly as long as we hoped. But anyway, we can fix little scratches. So in general, you can think of the set of all possible sequences as a kind of high-dimensional cube. Here I've drawn a 3-dimensional one on a 2-dimensional screen, but think in 7 dimensions for these. And then all these different code words are all fairly far from each other, so that if this is the true message and we have a little bit of noise, we can tell where we started and fix the noise. That's the idea behind an error-correcting code. All right, so far, and in fact, in general, finding this closest code word, though, it can be hard. It can be computationally hard. Now, that doesn't sound useful. You don't want it to be hard for the CD and your for the computer and your CD player to fix the scratches. Some error-correcting codes are easy to fix, those are the ones we use for CDs, but others are hard. All right, good. So where's the secrecy? So here's the idea. Alice has an error-correcting code for which she can easily fix the errors. But she doesn't share that with the world. Instead, she shares a kind of scrambled version of it where she has taken this high-dimensional crystal of code words and mushed it around and twirled it around and rotated it, and she publishes that. Okay? I can explain what I mean in the Q&A if you really want. So then Bob composes his message in that scrambled code that she publishes. He then deliberately adds a little bit of noise. And the idea is that Alice can untwist it and fix that noise, but an eavesdropper can't. That's the hope, okay? Because this general problem of fixing the noise in an error-correcting code can be computationally hard. All right, how can we crack this with quantum computers? This cryptosystem has been around for 30 years. It's not in wide use because RSA is so much easier to implement, but it's still around there in literature. Can we unscramble this? So can you take Alice's published scrambled code and figure out how to unscramble it to make it easy to fix the noise and thus decrypt Bob's messages? Well, there's another problem which is mathematically similar. I show you 2 networks, or graphs as mathematicians like to say. Each one is a bunch of nodes and a bunch of links between the nodes, and I ask you, is there a way to rearrange the nodes of this network so that it looks just like that one? Are these 2 networks actually the same? Do they have the same structure except for a rearrangement of the nodes? I'll let you ponder that for another few seconds. So we do not know how to solve this problem on standard computers. And we think it might be outside that class P, although we're not sure. Because the point is, if n is 100 or 1,000 here, there's an astronomical number of different rearrangements we could try. So we had better do something a lot smarter than just trying them all. And so far, except in special cases, we don't know such a method. This problem for the connoisseurs is called graph isomorphism. So these scramblings or rearrangements, we call them permutations in mathematics, and you can multiply permutations together, but unlike with normal numbers, x times y and y times x are not the same. If first you switch the first and second thing, and then you switch the second and third thing, you don't get the same result as if you do those things in the opposite order. It's just like with a Rubik's Cube. If you twist the top and then the side, you don't get the same result as if you twist the side and then the top. So this is a kind of non-commutative multiplication. The commutative law is when xy equals yx, but this is a non-commutative multiplication. That makes it more complicated. So it turns out there's a beautiful field in mathematics called group representation theory that tells you that anytime you're permuting things, there's some way in which you can think of those permutations as rotating and reflecting things in a high-dimensional space. So here, for instance, is a three-dimensional representation of not all of them, but half of the permutations of 5 objects. So if I want to change yellow to white, white to red, red to blue, blue to green, and green to yellow, I can do that by rotating this beautiful origami thing. And that gives me a way to represent those permutations in this three-dimensional space. So why am I telling you all this? I'm telling you all this because in the years after Shor's algorithm was discovered, people were very hopeful that we could solve this graph isomorphism problem with a similar approach. Here's the idea. So Emmy Noether, one of my heroes, discovered that an enormous amount of physics is really about the symmetries of the world. Okay? So if you remember your freshman physics, why is momentum conserved? Oh, well, it has to do with equal and opposite forces, so things cancel out and the total momentum stays the same. All right, good. Why is angular momentum conserved? Oh, it's complicated. There are these torques and there's a cross product and I forget how it worked, but things canceled out again. Well, that's what we show you in freshman physics. So if you stick around, in like the third year or so, we show you the good stuff. And it's a hazing ritual, like most college educations, and we show you that the reason why angular momentum is conserved is literally because if you take the universe and rotate it a couple of degrees this way, its total energy stays the same. That's why angular momentum is conserved. Momentum is conserved because if you take the entire universe and shift it 3 paces to the right, the energy is the same. All of these conservation laws we learn are really about the symmetries of the world. That was Noether's discovery. You could phrase all of Einstein, all of his work on relativity, by saying that the symmetries of the world are not what Galileo thought they were. When I'm heading in that direction at a certain speed, the way I perceive space and time is not quite what Galileo thought. And when you figure out the correct symmetries of the world, you've really learned, at least from a point of view of elementary physics, you've learned almost all of physics. Okay, I hope I haven't offended too many people in the world, but in the room, but you know what I mean, right? You're with me? Okay, good. So periodicity is a kind of symmetry. What does symmetry mean? I mean, when we say a square is symmetric, we mean we can rotate it 90 degrees and it looks the same. Periodicity is something that, nice special effect, right? If you shift it over, it looks the same. So I already told you that quantum computers can detect periodicity. Well, there are lots of higher dimensional symmetries as well, from Escher's tilings, this is a copyright image, just so you know, to the rotations and reflections of some polyhedron. So the idea is that if quantum computers can detect these sorts of symmetries as well, then they could tell whether 2 graphs are isomorphic, whether we can rearrange them to look like each other, and they could unscramble Alice's code in this alternate cryptosystem I told you about. Well, turns out this doesn't work. My friends and I thought we would have people chasing us in the street demanding our autograph. That didn't quite happen. It turns out that the possible ways that Alice can scramble her code correspond to rotations and reflections in a very high dimensional space. And if you try to follow Shor's algorithm and to perceive those higher dimensional symmetries, it doesn't work. No matter what you do, no matter what quantum measurement you perform on the state you get out of that, you get almost identical results no matter what scrambling Alice used, or even if she chose a completely random code. And so we learn next to nothing about how to crack her code. So this fails to break this cryptosystem. The good news is maybe this cryptosystem will be secure, even in a world where quantum computers are commonplace. Now, of course, this is a little bit of a funny argument, right? What I've told you is that we can't break a cryptosystem that no one is currently using computers that no one has yet built, at least not using the methods that we've thought of so far. That's not terribly comforting, or it might just seem out there. And you know, this is the difficulty with cryptography. If I want to show you that I can solve a problem, that I can break a cryptosystem, all I need to do is show you a way to do it and prove that it works. If I want to show that you can't solve a certain problem and that you can't break a certain cryptosystem, this is much, much harder. I have to somehow argue with you or reason with you about all possible algorithms, all possible approaches, and prove to you that none of them work. And this is extremely challenging. And this is why many problems about computational complexity are still wide open. We don't know for sure that there's no way to zoom in on the needles in those haystacks. We just haven't been able to do it so far. And in fact, we've been surprised before. There have been problems that we thought were hard that turned out to be much easier because a clever person came along and thought of a new method. But at least it would have to use some new ideas. All right, there's one other form of communication that in this case, quantum mechanics works in our favor. So let's put an eavesdropper in between Alice and Bob. And I'm sorry to tell you that yes, cryptographers often call the eavesdropper Eve. As always, Eve gets a bad rap. So you have all heard that you can't measure a quantum system, you can't observe a quantum system without disturbing it. So in 1984, Charles Bennett and Gilles Brassard came up with a very nice scheme. They said, well, if Alice sends Bob a string of bits, they can actually tell whether or not she listened into it. Because in order to listen in, she must observe it. And if she observes it, she disturbs it, and it destroys some of the information. And then Alice can send Bob some additional information to kind of check to see if it got through unmolested. Now, this is quite bizarre, right? I mean, in classical communication, if I intercept a note from you to your confederate, I can write down a copy for my own use, pass the note on, have your friend blithely think that the message got through, and then do nasty, horrible things in the service of my nation state against your nation state. Okay, but in the quantum world, you cannot just make a copy of something. If you observe it, you affect it. So this is very interesting. So what this means is that Alice and Bob can confirm that their message got through okay without Eve even being able to read it. Once they confirm that, then they can use that message as a secret key, for instance, as a OneTime Pad in this quantum walnut for their further communication. This has already been implemented in some fairly impressive settings. It's been done over 200 miles of optical fiber, some of which was admittedly rolled up in a box, but it was still very long. It's been done using a laser through the air over 144 kilometers between two of the Canary Islands, and as a kind of proof of concept, it's been used in Switzerland to transfer bank transfers and election results. It's much easier to do this than a full-blown quantum computer, And so this technology is fairly close to being commercialized. All right, so can we build these things? You know, how much should we worry? Shall we just keep using RSA cryptography? Is quantum computing around the corner? Well, this is what the first transistor looked like, and it was kind of clunky, and it took up a lot of space. And this is what transistors look like now, or actually a few years ago, and now we're making transistors that are thinner than a human hair. And this is what the first integrated circuit looked like. It was stuck to some things with glue, and this is what they look like now. So we are getting better at doing this, building very tiny things, and we're rapidly gaining an ability to move single atoms and even single electrons around. So here is a picture from right here at the University of Wisconsin. Here is a picture of atoms sitting in an ion trap. These are individual atoms. They're just single atoms. Wouldn't you love to go back and tell Democritus that, yes, things really are made of atoms. Look, there they are. He would probably say, oh, you've taken all the fun out of philosophy. I figured this out in my armchair. You need a laboratory. All right, but it's, you know, it'd be nice to show him anyway. So building quantum computers is tricky because just as Eve's observation alters and destroys some of the information that was going from Alice to Bob, here you have a nice quantum computer, and it has these delicate electrons and nuclei in this beautiful superposition. They're in two different places at once, or they're pointing both up and down at once with their little magnetic fields. And a stray radio wave comes in and interacts with them. That stray environment, in essence, measures them, not on purpose like Eve, but this tends to destroy quantum information. It's called decoherence. So it's tricky. To maintain a quantum state, you have to shield it from these stray interactions for a long time. On the other hand, you can't shield it completely because to get anything done in your computer, it has to interact at least with the other things in the computer. And this causes a difficult balancing act. So on the other hand, I don't think it's impossible. So here are some quantum devices, also from here at Wisconsin, where people, some of whom are in the room, have succeeded in trapping, for instance, single electrons in particular places, coax them into hopping back and forth at the right times, or to flipping their spin at the right times. Or they've, you know, frozen a little lattice of cesium atoms floating in the middle of space, hovering there in a laser, and they can get these atoms to talk to each other, but only when they want them to. So it's early days yet, but I don't see anything impossible about this. I think it's probably easier than building the space elevator. So I expect quantum computers in our lifetime if it's a priority. It will take a little while for them to go from looking like this to looking like that. But we should think about them. Moreover, I just want to quote Scott Aronson, since we heard from him earlier. So he says, I don't care whether quantum computers are ever going to be built. He says, after all, computers play the same role in understanding computation as clocks and trains play in understanding relativity. What he wants to know is what's the fundamental nature of our universe, and one of the fundamental questions we can ask are, what problems can we solve using the physics of our universe? What problems are easy and what problems are hard? Thinking about quantum computing helps us understand the answer to that question, whether or not we ever get around to actually building them. Thank you very much. Now I'm embarrassed, you know, but it is my last slide. I am prepared to take questions.
And if you can just wait until you have a microphone in your hand to ask it.
If there are any.
So you could say that like quantum computers are one of the most powerful like computers we could come up with like with our current understanding of physics. Like if that stays the same, is it possible to say that if something can't be broken by a quantum computer, it just can't be broken ever? Like given how our understanding, like if some new theory came along, like we maybe come up with a better computer, but.
Right. So I guess if can I rephrase your question? Can I rephrase your question by asking, are quantum computers what we think are the ultimate computers that we can build in this universe with these laws of physics? I mean, I think people are not entirely sure. So Richard Feynman was really interested in the question of, if you take a 1 meter box and 1 meter on a side and think about all the physics that's happening there within 1 second, he asked, is all of that a finite amount of information processing all the particles and all their interactions, or is it an infinite amount? And we don't actually know, right? So we don't know whether space and time at the very smallest scales are continuous or discrete or some more confusing quantum thing. And if space is continuous, then you could imagine that the more you zoom in, the more stuff is going on, so that actually an infinite amount of computation is happening in that box in that time. The question is still, though, can we harness it, right? We still would need to do some engineering with that, get an input into it, somehow address those ultimate degrees of freedom at smaller and smaller and faster scales, and then get the result back out. So that might be impossible to do. Even if nature is doing an infinite amount of computation, we might not be able to take advantage of that. There are some other kind of fanciful things. So one approach to computation is you place your friends or perhaps your graduate students in orbit around a black hole. You wave goodbye to them and you fall in. Now, so you may know that there's what's called a gravitational redshift. So as you get closer and closer to the event horizon of the black hole, time goes slower and slower for you. So the idea is that as you fall in, your students do an infinite amount of computation, or they and their descendants. And if and when they finally get the answer, they send you a message just before you're torn to pieces in the black hole, and you put your foot on the accelerator, and maybe you get out, or maybe you just go to your grave, knowing the answer, which might be worth it. But you can see the game that we're playing there. We're trying to squeeze an infinite amount of time into the universe using, in that case, general relativity. And of course, this doesn't really work, because meanwhile, as you're falling in, the black hole is slowly evaporating. It doesn't last forever. A stray photon will also get blue shifted infinitely and destroy you if you're really close to the event horizon. And besides, your students will run out of pizza. So I think the basic question is there some way to fit an infinite amount of work, of information processing, into the universe in finite time and finite space? And my guess is no, but we don't really know. This is ultimately a question about physics it's ultimately an empirical question. Yes. By the way, if my talk was too elementary, I hope that meant you were taking notes and that you're going to tell your kids. I mean, you could at least do what I do with my daughter, which is send each other messages in like the little Pigpen cipher or something like that. That's a good start. Yes, back there.
Cris, thank you for a great talk, and I didn't find it too elementary personally.
Good.
So I've read press reports on commercially available quantum computers, which you decidedly did not mention. And there appears to be some controversy as to whether they actually are quantum computers. So my question is, if somebody builds a quantum computer, how will we know?
This is an excellent question. So you're referring, I assume, to a company called D-Wave. And D-Wave has had a fascinating history. So at first, they didn't even let anybody look inside their boxes. And a lot of us thought that maybe there was a little person inside the box. More recently, they've really let some reputable people play with their machines and do experiments on them, including some physicists whose opinion I trust. like Daniel Lidar at USC. So the D-Wave machine is not really trying to do quite the same things we were talking about. So imagine that you're trying to solve some difficult optimization problem. There's a lot of different solutions. Each solution has a cost. You want to find the solution with the lowest cost. So there's a kind of physicsy way to solve this problem, which is you wire things up so that the cost is literally the energy of your system, and then you cool it down, trying to get it to find the lowest energy state. And if it does that, hopefully, that's your solution. All sorts of things can go wrong. It can get stuck in what's called a local optimum, a kind of little bowl where the real solution is over there. It has a much lower height, but it's kind of stuck here, and anything it does to try to change things a little bit only makes them worse, so it gets stuck there. Well, maybe in quantum mechanics it could tunnel through this hillside and find that lower place. So that's kind of the idea. So D-Wave has built this interesting machine. It's on a chip where they have a quantum device, and the idea is that you go from a very simple flat landscape of energy and you slowly turn on the effect of the problem you're trying to solve, and hopefully, if all goes well, you'll end up in that lowest point. There isn't really consensus about whether it does this. So what my impression is that their machine is doing something quantum, but part of the problem is that there have been so many overblown reports in the press, many of which I think are overblown deliberately by them, that it's sort of hard to disentangle the kind of careful academic work from the press claims. I personally look at the progress that groups at universities like this are doing, and I feel like other technologies will probably succeed. Getting to your question, if I build a quantum computer, how can you tell it works? Well, this is tricky, right? So I'm going to quote Scott Aronson again. So remember that class I called NP. That was the class of problems where if I show you the solution, you can check that it's correct. Well, it appears that some of the things quantum computers can do are not in that class, which means that we don't have such a good ability to actually check them. So this creates an interesting philosophical conundrum. How would you verify claims that a quantum computer actually works? So presumably what we would do is take some problems that we can check but very laboriously. So factoring you can check, but we would take other sorts of problems that, if we put enough work into them, we can check them. And then as we go past, if we confirm that it works on these small examples, that at some point we would have to trust that it works on larger ones. So we poor classical creatures don't really have the computational power to check quantum things. In fact, in computer science, I can't resist. Since we already introduced Alice and Bob and Eve, there are two more characters, Arthur and Merlin. Arthur is a poor polynomial time schlub. He's a mere mortal like us. Merlin has godlike computational power. So in computer science, we often imagine a conversation where Merlin says, the answer is this, and Arthur says, wow, can you prove that to me? Not that I don't trust you, but can you show me how that works? And for some problems, there is a proof that Merlin can present that Arthur can understand. But for other problems, there's nothing Merlin can do. There's no way Arthur can possibly comprehend why this is the solution. So I think that gets into a nice question about the scientific method. Can we, as classical scientists, really learn how quantum things work? That might have been a longer answer than you really wanted, but there you go. Yes? I think you have an answer in mind.
Cris, could you repeat the question for everybody?
Okay, so the question was, is there any evidence that quantum computing is happening somehow in nature? I'm not an expert on this. I don't know about quantum computing per se, but there is a lot of evidence that some natural systems have evolved to use quantum effects in chemistry. I mean, I expect there are people here who can correct me if I miss my mark, but even the transfer of ions across a junction from one neuron to another involves some quantum tunneling, some hopping. A lot of important chemistry happens because electrons are not in just one place, but are kind of distributed in a quantum fashion in multiple places in the molecule. But one of the more famous examples that people have talked about recently is photosynthesis. So there's a protein complex in leaves and chlorophyll, so that when a photon comes in, the energy from that photon kind of rattles around the molecule, and hopefully it gets transferred to ATP so that the plant can use that to make sugar. And there are multiple paths by which it can get there. And the claim is, and I've heard this claim made by very reputable folks, so I believe it. So the claim is that if you look at those different paths, it seems to have evolved so that the energy from the photon arrives in phase and is thus transferred efficiently, rather than getting a lot of cancellation and having it arrive only, less efficiently. So I guess we can argue about whether this is a transfer of information. It is certainly a transfer of energy, and I think the line between energy and information is not so easy to draw. Then there's the claim by people like Roger Penrose that our brains are doing something quantum, and that because they're doing something quantum, and quantum things are really complicated, and that this is why we can think things that computers can't, and why we're conscious, and that it is something to do with quantum gravity too. And as maybe you can tell, I don't really find these ideas convincing. It seems to me that Penrose is saying there are two things in the world we really don't understand: quantum gravity and consciousness. They've got to be connected somehow. So I regret to say I've become very orthodox and curmudgeonly in my old age. I think the brain is a very warm, wet place, and I'm skeptical that we are doing thinking in a quantum way. We're obviously doing thinking in some unbelievably amazing way, but whether quantum mechanics is really involved in it, I'm a little skeptical. Although one of my favorite authors, Kim Stanley Robinson, got into the whole thing about microtubules, and this is how people in his Mars books lived a really long time. But anyway. Shall we take one more question?
As a software engineer, I'm curious about your take on debugging a quantum computer program. Is it infinitely difficult, utterly trivial, or is it an artifact of the von Neumann architecture and therefore irrelevant?
Oh, I'm glad you mentioned von Neumann. I was supposed to mention him, right? Well, I think this gets back to his question about, can we check the results of a quantum computer? Could you even tell whether a bug exists? So at a small scale, we can debug quantum hardware by doing the physics and figuring out what signals we should get out of it. But as you well know, as a software engineer, there's a huge gap in our ability to do engineering reliably between the hardware and high-level software. So I expect that if we actually get quantum computers in our hands, that for a long time we'll program them kind of in machine language, right? Sort of the way we programmed the very earliest digital computers. But people are already starting to think about what a high-level quantum programming language would look like. So should the program itself, for instance, be a superposition of this line of code and that line of code? I mean, how would that work? And I expect that if this comes to pass, we'll have a lot of I hate to use this word, but paradigm shifting to do. You know, just as right now we're struggling to teach our students how to program highly parallel computers, right? Because we're so used to the idea of serial computers, von Neumann computers, that do one thing at a time. So program is do this, then do that a million times, then do that, unless this is true, and do that. And the fact that we now have computers that have multiple processors that can do many things simultaneously, it's a struggle, certainly for people of my generation, to figure out how to use those processors to their best ability, to look at the problem you're trying to solve and to realize, oh, I can do all these things simultaneously. Sometimes it's obvious, but sometimes it's tricky. So then people are building all these amazing middleware compilers that look at our programs and, unbeknownst to us, recognize that certain things can be done at the same time. They don't have to be, you don't have to do this and then that. And so they put these things on our 4 or 8 core laptops without us having to think about it. But presumably, eventually, our idea of what it means to write a program will have to change if we want to take full advantage of quantum computers.
Thank you, Cris. Thank you very much.